Hello everyone, this is Joshna from third year CSC A section in Adishankara Institute of Technology. Today I am giving Tech Talk presentation in MCA. The topics are differentiate between RISC and CISC architectures, important designs rules of RISC philosophy, different features of ARM instruction set that make it suitable for embedded applications. First, difference between CISC and RISC. CISC and RISC. CISC is a compressed instruction set computer. RISC is a request instruction set computer. CISC can emphasize on hardware. RISC can emphasize on software. Multiple instruction sizes and formats are present in CISC. Instructions of same set with a few formats are present in RISC. CISC contains less registers. CISC contains more registers. CISC contains more addressing modes, but RISC contains fewer addressing modes. CISC is extensive use of microprogramming. RISC is complexity in compiler. Instructions take a varying amount of cycle time, that is CISC. In RISC, instructions take one cycle time. In CISC, pipelining is difficult. In RISC, pipelining is easy. Next, important design rules of RISC philosophy. Here, RISC and CISC philosophers, compiler and processor can give the complexity and show the emphasis hardware and software. CISC versus RISC. CISC emphasizes hardware complexity. RISC emphasizes compiler complexity. The RISC philosophy is implemented with four major design rules: instructions, pipelines, registers, load store architecture. Instructions. RISC processors have a reduced number of instruction classes. These classes provide simple operations that can each execute in a single cycle. The compiler or programmer synthesizes complicated operations by combining several simple instructions. Each instruction is a fixed length to allow the pipeline to fetch future instructions before decoding the current instruction. In contrast, in CISC processor, the instructions are often of variable size and take many cycles to execute. Next, pipelines. The processing of instructions is broken down into smaller units that can be executed in parallel by pipelining. Ideally, the pipeline advances by one step on each cycle for maximum throughput. Instructions can be decoded in one pipeline stage. There is no need for an instruction to be executed by a mini program called microcode as an CISC processor. Next, registers. RISC machines have a large general purpose register set. Any register can contain either data or an address. Registers acts as the fast local memory store for all data processing operations. In contrast, CISC processors have dedicated registers for specific purposes. Next, load store architecture. The processor operates on data held in registers. Separate load and store instructions transfer data between the register bank and external memory. Memory access are costly, so separating memory access from data processing provides an advantage because you can use data items held in the register bank multiple times without needing multiple memory accessing. In contrast, with a CISC design, the data processing operations can act on memory directly. Next, the different features of ARM instruction set that make it suitable for embedded applications. The ARM instructions set differs from the pure RISC definition in several ways that make the ARM instruction set suitable for embedded applications. Variable cycle execution for certain instructions. Not every ARM instruction executes in a single cycle. For example, load store multiple instructions vary in the number of execution cycles depending upon the number of registers being transferred. The transfer can occur on sequential memory address, which increases performance since sequential memory access are often faster than random accesses. Code density is also improved since multiple register transfers are common operations at the start and end of functions. Inline parallel shifter leading to more complex instruction. The inline barrel shifter is a hardware component that pre-processes one of the input registers before it is used by an instruction. It expands the capability of many instructions to improve core performance and code density. Next, thumb 16-bit instruction set. ARM enhanced the processor core by adding a second 16-bit instruction set called thumb that permits the ARM core to execute either 16 or 32-bit instruction. The 16-bit instruction improve code density by about 30% over 32-bit fixed length instructions. Next, conditional execution. An instruction is only executed when a specific condition has been satisfied. This feature improves performance and code density by reducing branch instructions. Enhanced instructions. The enhanced digital signal processor DSP instructions were added to the standard ARM instructions set to support fast 16 bit multiplier operations and saturations. These instructions allow a faster performing ARM processor in some cases to replace the traditional combinations of a processor plus a DSP. That's all. Thank you for giving this wonderful opportunity to me.